Does it make sense? All right. So, now that we have the small signal model, I mean, the next thing we do is what did we do in the MOSFET? We figured out how to bias the transistor, right? The what is when recall that when we were working with MOS transistors, the first bias circuit that we used was this, okay, and what is the problem with this? So, either changes in VDD or changes in temperature will cause the drain current to vary wildly, right? And that is because, I mean, the transconductance of the device is large. That basically means that a small change in the gate voltage will lead to a large change in the the drain current. I mean, that is the whole idea behind amplification, right. So, you want a small change in gate voltage to result in a large change in current, which you can then push through a resistor to get a large voltage at the output. Now, if this was remember, and then we said this is a bad idea. In a bipolar transistor, if it was a bad idea, in the case of a MOS transistor, right, what comment can we make about the bipolar transistor? So, if it was a bad idea in a MOS transistor where the transconductance in a MOS transistor is proportional to, when it is operating in saturation, it is proportional to, let us say you have a drain current I flowing in the transistor, the transconductance is proportional to, yeah. So, the transconductance is proportional to square root I, okay. In a bipolar transistor it is proportional to I, right. So, basically as you can see, therefore, the transconductance of a MOS of a bipolar transistor is much stronger than that in a MOS device, and that basically means that if it is a bad idea in the MOS case, it is a terrible idea in the case of a bipolar transistor. So, you should never do this. All right, because tiny changes in the base emitter voltage, it can cause a large change in the current. Another point is that another source of problems with the bipolar case is that the base is also now drawing current. So, apart from the variation of VDD and variation of R1 and R2, you now also have to worry about the base current, because I mean, if you draw base current out from here, what comment can you make about that potential? And ideally, it is supposed to be VDD times R2 by R1 plus R2. Now, you start pulling base current out of that node, the voltage will drop, right. So, and it turns out that beta is not very well controlled. So, it is the same transistor can exhibit different betas on different days, right, depending on temperature and all this stuff. Those of you who have done a device class, you probably all know about this already, but the point is that so you should never rely on whenever you are doing circuit design, you should never rely on the fact that your transistor has got a beta of 98, okay. And if beta is 99, if your whole circuit falls apart, that basically means that this is a bad design. You understand? All right. So, so what did we do to fix this problem of biasing in the MOS case? Well, we use negative feedback, okay, and the first thing that we did was use a current mirror, and that is something that we can do here too. And just like in the MOSFET, there are 4 fundamental ways of establishing the quiescent operating point, right. through negative feedback. What is it? You can measure the collector current, you can measure the emitter current, and and we go with the notion that the collector current and emitter current are almost the same. Okay. So, you can measure the current in the transistor, the quiescent current of the transistor in two different ways, and you can adjust the base emitter voltage in two different ways. You can either keep the base fixed and vary the emitter voltage, or keep the emitter fixed and vary the base voltage, and you basically go and that is basically what causes the feedback action to occur. So, there are, you can think of at least 4 ways in which you can stabilize the bias of the transistor, bipolar transistor, just like we did in the MOS case, right. So, all these circuits are pretty much the same. So, there is no point in beating a dead horse. So, basically here is, let me quickly only point out the differences. So, here is the bipolar transistor current mirror, okay, and there is a small catch here. In the MOS case, the gates were not drawing any current, okay. So, the reflected current in the mirror would be exactly the same as what is pushed in. Now, there is a slight difference, and that has to do with the base current. So, this let us call this I x. Okay. So, what is the current what is this current? What is that current there? It is going to be exactly I x, because both transistors Q1 and Q2 have the same base emitter voltage. So, they will have the same collector current. So, and what is the base current of Q1? What is IC? The collector current of Q1 is I x. So, this current is going to be I x by beta. This is also going to be I x by beta. So, this current is going to be 2 I x by beta. So, how is I x now related to I c therefore? I c must therefore be equal to I x plus I 2 over beta, which therefore means that I x is I c by 1 plus 2 by beta. All right. So, basically you can see that there will be some small error in the current in Q2, collector current in Q2, it will not be exactly I c, it will be slightly smaller, because some of the current I c has gone into to support the base current. So, in a MOS transistor based current mirror, you could just simply copy, you could have 100 transistors sensing the same voltage, and all the 100 transistors would at least ideally give you the same current without any. Now, what comment can we make about when you have, let us say 10 transistors mirroring off of this Q1? The error will go on getting increased, because so basically now if you have 100 transistors feeding off that single node, then you will have 100 base currents that you have to support, and so then the accuracy of the mirror will become very poor. Okay. So, what do we do to fix this problem? Any suggestions? Well, you can't avoid these base currents. These base currents can't be avoided, right? But the problem is that base current is getting subtracted out of IC. That is the problem, correct. So, what is this short doing actually? this base emitter, collector base short, what is that doing? I mean, what is its job? How did we get the current mirror? We compare the collector current with the reference current, and go and kick the base voltage in the right direction, correct. So, basically if this goes up, this voltage must go up. The easiest thing to do in the MOS case was simply short these two, right, and shorting did not affect any. We want the voltage of the base to be the same as that of the collector, right. In the MOS case, that was very easy. We just created a short circuit, and because the gate did not draw any current, we were okay, all right. But now the gate actually draws current. So, what do you think? We want the base voltage to be the same as the collector voltage, but we do not want the base current to come from IC. So, what do you, in principle, what will we do? You want the voltage there to be the same as the voltage here, but you do not want that load current to be supplied from here. What will you put between the two nodes? Okay, let me, this is V in, this is V O. We want V out to be the same as V in, but we do not want this current through R L to be drawn from the input. What will you put? Voltage controlled voltage source. So, basically the principle is that if you put a voltage controlled voltage source here, then all this current will be supplied by the VCVS, right, and this current will be very small. Okay. Now, how do we realize the voltage controlled voltage source? Well, if if you how do you realize a voltage controlled voltage source with MOS transistors? What is the simplest VCVS that you know? Common drain. So, here the analog will be common collector, right. So, basically okay. And now all this current, if you have 100 transistors here, all the base current will be supplied by the common collector stage, right. And so, for this current will be, what will this current be? It will be smaller by a factor of, beta. So, let us in this case let us call the this is Ix over beta, this is also Ix over beta. So, this is 2 Ix over beta. What is the base current therefore? 2 Ix over roughly beta square, but actually it is, there will be another factor of beta by beta plus 1, which I am neglecting. Okay. So, you can see therefore that instead of the new Ix will be Ic by 1 plus 2 beta square. Okay. So, now you have the error has been reduced by an order of magnitude. All right. Okay. So, that was one way of biasing the transistor. The other way of biasing the transistor is to keep the base voltage fixed, and vary the emitter voltage, I mean compare the measure the current in the emitter and vary the emitter voltage, so that the emitter current is the same as the reference current. So, again I will not go through the math all over again or the intuition all over again. You just stick a current source IRF in the emitter and you are good to go. All right. So, what is the assuming the beta is very large, what is the potential here? So, this is nothing but VDD times R2 by R1 plus R2, and what therefore will this potential be? Yeah, minus VB. VB nominal for a forward biased, for an active transistor operating in the active region is 0.65 volts. So, this is going to be VDD times R2 by R1 plus R2 minus 0.65 volts. Okay. All right. Now, if you can't afford a current source, what will you do? Put a resistor there. Okay. So, this is a, so let us call this RE. So, what is the current, collector current? So, this divided by RE is the collector current. Okay. And again, what constitutes a large, so ideally RE must be infinity, you can't make RE infinity. So, it has to be large. What is the meaning of large? Pardon? So, the GM RE must be much greater than 1. Okay. And what is GM? IC over VT. So, this times RE must be much greater than 1, which basically means that IC times RE must be much larger than VT. All right. And then the other two ways of stabilizing the bias, you can figure it out yourselves. There is really nothing very much there, right. And likewise, I mean, so this covers the biasing of NPN transistors, and as usual, then we went on to bias the transistor and then look at the 4 basic amplifiers. So, this is the small signal equivalent of the common source amplifier. Okay. Now, the fact that the transistor has got a non-zero Y11 means that what is the voltage at the base now? The incremental voltage at the base is beta by GM over beta over GM plus RS, okay, times Vi. So, the voltage at the output is nothing but minus beta over GM by beta over GM plus RS times R. This is the common emitter amplifier. Okay. And in principle, the GM of this transistor, I mean the the transistor can be made very large by pumping, by biasing it with a sufficiently large quiescent current. So, then we said let us make the 4 control sources. When we were talking about the MOS case, we said let us make the 4 control sources. So, that is basically this is Vi, this is some Rs, right. This is the voltage controlled, sorry, this is RL, and this is the common. Are you saying something? Oh, sorry, yeah, indeed, yeah, times Gm. Okay, so this is the common collector amplifier, which is analogous to the common drain amplifier. It gives you an incremental voltage controlled, or attempts to give you an incremental voltage controlled voltage source with unity gain. Okay, and so the incremental to find one again one departure from the MOS transistor is basically that the gate current there was 0. So, the input impedance was infinite as seen by the source. Now, it is no longer so. So, let us try and find what the input impedance is. So, R in, as you can see, well, we have beta over Gm this is Gm times Vx minus Vo, all right. Okay. Another way of thinking about it is, if this is Ix, what is this current? Beta times Ix. So, what is the current flowing through RL? 1 plus beta times Ix. So, what is Vx in terms of Ix? Vx is nothing but beta over Gm times Ix plus 1 plus beta times RL times Ix. So, the input resistance Rin is it is beta plus 1 times RL plus beta over G. Okay. So, sanity check, of course, as beta tends to infinity, input impedance tends to infinity, but in practice that's not really the case. With finite beta, you will have a large impedance, but but it is not infinite. Okay, what comment can we make about the gain? we know Rin. So, Vx is basically Rin by Rin plus Rs times Vi, okay, and current flowing in Ix is nothing but Vx by Rin, okay. That current will get multiplied by beta plus 1, and that is the current flowing in the emitter. The emitter current into RL is the output, right. So, this current into beta plus 1 into RL is VO. So, VO by Vx therefore is nothing but beta plus 1 RL divided by Rin, which is beta plus 1 RL plus beta over Gm, which is written as RL by RL plus beta over beta plus 1 times 1 over Gm. So, this quantity, it turns out that if you keep working out these problems, you keep getting this this quantity all the time, 1 over Gm times beta over beta plus 1, okay. And this is often called small r sub e, okay. And the motivation why this comes about, I think, is it should be is quite simple to see. Remember that this is beta over Gm and this is Gm VBE all right. And so, this current or IB is and this is beta times IB, all right. So, one could alternatively push this resistor through this node. I mean, what is the earlier? So, this is beta over Gm. So, what is the drop between the base and emitter? It's IB times beta over Gm. So, one could in principle move this resistance here okay. I mean, what is the difference between that branch and this branch? The current flowing here is IB, the current flowing here is beta plus 1 times IB. So, if you want the same drop between the base and emitter as you had earlier, what should you choose for RE? The current flowing in RE is beta plus 1 times higher. So, the resistance must be, yeah. So, earlier the resistance was beta over Gm. So, this must be beta over beta plus 1 times Gm. Okay. I mean, this is just simply circuit manipulation, there is nothing holy about this, but in many cases this will give you, it might result in mildly simplified circuit schematic, I mean circuit analysis. Okay. A case in point is the circuit that we have been seeing. So, for the common collector amplifier, This is the transistor. So, this is IB, this is beta plus 1 times IB, okay. And what is the output voltage VO? Sorry, beta IB, correct. No, what is this voltage? That is V in. So, what is the output voltage? Is nothing but simply RL by RL plus RE times V in, right, which is what we got, above, right. So, this is nothing but RE, okay. So, people, I mean, keep interchangeably using this equivalent or the other depending on convenience, and it is I mean, it's good to know both these things, but for the final answer that you get will be with the same or should be the same in both cases. So, the common collector amplifier is analogous to the common drain. It behaves like a incremental voltage controlled voltage source with a gain of 1. That makes sense, folks? Okay. Then, so that is the voltage controlled voltage source. The voltage controlled current source is very similar. So, this is Vi, okay. Now, what is the incremental current flowing here? Pardon? Yeah. So, basically remember that we replace the transistor, just now we replace the transistor with this equivalent. So, if this is IB, this is beta times IB, and there is small re in the model, right. This is what we just did just now, and this is I. Okay. All right. So, now stare at it and tell me what is this current? Vi over capital RE by, I mean Vi over capital RE plus small re, or of this current how much will I out be? How much of it will flow through I out? Yeah. So, basically you can see that the collector current is beta times the base current. So, the current I out will be Vi by capital RE plus small re times beta by beta plus 1. So, if you want to be hair splittingly accurate, you do this, but for all practical purposes this is simply Vi over capital RE plus small re. Okay, and if capital RE is much larger than small re, then it's pretty much the same as Vi by capital R. Okay, so this is the voltage controlled current source.